Hello everyone, welcome back to another Geostats lecture video. And in this lecture video, we're going to go through the exploratory data analysis portion of setting up a spatial lag model in R. Now, the exploratory data analysis phase is going to look very similar to what you would see for a traditional regression, with a couple of key differences. The first is we're not going to do anything with training and testing data, because spatial models, sort of by their definition, are networked, right? That's one of the things that it means to be a spatial model, is that we're networking the data together spatially. So it doesn't really make a whole ton of sense to pull observations out, right? Because it's going to mess up that network. And so we're actually not going to bother with prediction, which means we're not going to bother with subsetting the data. The other big difference is that because we're talking about spatial models, we're just going to do some quick EDA in terms of looking at the autocorrelation, which is something that we didn't really concern ourselves with last time. Other than that, it's going to be very similar. So we're going to have two variables. We're going to have the lung cancer rate, which is going to be our dependent variable, and then we're going to have the smoking rate, which is going to be our independent variable. So we're going to be looking at both of those in terms of their relationships, normality, and spatial autocorrelation. So let's go ahead and just really quickly examine the dependent variable. So this is going to be that CNCR rate. So the first thing that we want to do is we always want to check for normality. And what I like to do is before running anything with Shapiro Wilkes, I just like to do a quick histogram. So this is going to be pen_UTM at data $ cancer rate, or CNCR rate. Not rate 0, rate. So if we run that line of code, you'll see that we get this histogram, and it actually appears to be pretty well normally distributed. Something else we can do is we can run a QQ plot. I prefer to use the ggplot2 implementation, so that's what we're going to do, ggplot, and then we're going to have this equal ggplot. Ggplot requires data, and it requires a mapping. The data is going to be the data that we're working with. In this case, it's going to be pen UTM at data. And the mapping, again, that's that aesthetic that tells us what variables are going to be driving what properties of the graph. So in this case, we want, because we're going to be making a QQ plot, we want to pass in sample, and we want the sample to be that CNCR_rate. Okay. Then we want to add an additional geom_QQ and a geom_QQ line. Sorry, geom_QQ_ line. So if we run that, could not find the function ggplot. Okay. So clearly, for some reason, it's not recognizing ggplot2. So we're just going to force the issue and do it that way. Which means we have to, anytime we see a ggplot function, we need to specify the package it's coming from. Okay. All right, so don't quite know why it was doing that, but we will worry about that later. So anyway, this is our QQ plot. And so again, the idea here is that we have this trend line here, and we want our data to be as close as possible to the trend line. And it looks like the vast majority of our data actually is. So this is another indication visually that we probably don't have too much of an issue with normality. And then the last test is going to be the Shapiro Wilkes test. And so that's going to come from the stats package, and it's Shapiro Dot Test. And the X in this case is going to be, again, that Penn UTM cancer rate. Okay, so if we run that, you'll see here that our value is actually statistically significant. So we really cannot reject the null hypothesis, which means that this data actually might have an issue with normality. But again, given the histogram and the QQ plot, I'm not too concerned about that right now. So we're going to move on as though it actually was normally distributed. Okay. So now that we've got that taken care of, we can do the same thing for the independent variable. I'm not going to bother making the QQ plot. I'm just going to quickly do a histogram of it. So this is going to be Penn underscore UTM at data $ smoking. And we need to remove that because that will break it. There we go. So this looks like this might actually have a little bit more of a problem, but let's just go ahead and quickly see what the Shapiro-Wilkes test has to say. So this is going to be not cancer rate, it's going to be instead, it's going to be smoking. You'll see that we have a much bigger issue with normality here than we did with the lung cancer rate. So what we're actually going to do is we're going to actually see if taking the log helps with the normality. So rather than this, I'm going to just quickly type in log. So if this improves normality, we will log it. If not, then for the sake of this demonstration, we will progress as normal. And that appears to have actually made it worse. So we are not going to bother doing a log transformation in this case. We're going to leave the data alone under the assumption that we're violating normality, but we're not too worried about that at the moment. So the next thing that we want to do is we want to go ahead and check for spatial autocorrelation. And the way that we do that is going to be, generally speaking, with Moran's I. So we're going to have to do three things. We're going to have to calculate the neighborhood values. We're going to have to calculate the spatial weights matrix, and then we're going to have to calculate Moran's I. So let's start with the NB. So we're going to call this Penn underscore NB. And this is going to be equal to that SPDEP package. And again, we're going to be using that function poly to NB. And this is going to create those neighborhood linkages. And so this has a function PL, which is the polygons that we want. And this is going to be Penn underscore UTM. Okay. And then for the spatial weights, right, this is going to be that SPDEP function NB to SW to list SW. It takes in that neighbors parameter, and this is the neighborhood linkages from the previous problem. Okay, so now we can calculate Moran's I. We're going to do Moran's I for both of them. The first one that we're going to do is we're going to do it for the cancer rate. So we will be doing Moran.test. X is the variable that we want to map. Again, this should hopefully be a review from our module on Moran's I. But again, just to go through this, right, Moran.test. This is going to be testing the randomization assumption so that the value is actually dependent on the location, right? We're testing against randomness. So if we have x equal, and in this case we're going to pass in our pen underscore UTM at data $, and then we're going to pass in cancer rate, and then our list W. This is going to be our pen underscore spatial weights. Okay. So if we run that, you'll see down here that we get a test statistic, Moran's I of 0.72, which again, if we wanted to directly interpret Moran's I, we would have to do the range to figure out the range of possible Moran's I values. But we can look up here at the p-value and see that the 0.05 alpha, this is actually not statistically significant. So again, right, so far everything we're seeing is pointing to the fact that our data is not normal and that we don't have autocorrelation. But we're going to move past this anyway, just to sort of show you how we would go through setting up these models. So that's for the cancer rate. Let's go ahead and do the exact same thing for the smoking rate. Okay, smoking. And then we'll pass in the list W, which again is going to be equal to pen underscore that. Okay. So you can see here that we actually do have, for smoking, a statistically significant Moran's I. Right, so we do have autocorrelation happening in the smoking rate. Okay. So then sort of the last thing to do is going to be check for relationship. Right, because the whole point of building this model doesn't mean a whole lot if we can sort of rule out any meaningful relationship beforehand. And so the way that we do that is we would do it with two things. The first is going to be a scatter plot. So we're going to just quickly plot. And then with a core from the stats package, a core dot test. And this is going to compare two vectors and give us the correlation coefficient. So in terms of checking the relationship, we're going to plot the x variable, which is going to be the smoking, against the y variable, which is going to be this cancer rate. So if we run that code, you'll see that we do kind of have something that looks like it might be a general linear trend, maybe. Right? We'll determine if there is in just a second, but we can do the same thing actually. We can determine if there's a relationship by running this core test. So if we run that, right, you'll see here that we have a correlation coefficient of 0.25. So it's not a great correlation coefficient in terms of a relationship, but you'll see here that the p-value is at least marginally statistically significant. So we shouldn't just ignore this outright. So this is actually going to be the variable that we're going to go forward with. So hopefully that made sense. Again, we're just simply going through the exploratory data analysis. So if any of this didn't make sense, I encourage you to go back, rewatch this video, maybe rewatch the parts of the video that these came from, because we haven't introduced anything new here. And as always, please reach out. Thank you.